Kia ora, welcome back. So in this video we're going to look at some examples, some word problems with the kinematic equations, just so we can get a sense for how they work in practice. So let's just dive straight in and see what happens, shall we? So first one, we have the example of an accelerating car. So when we've got a word problem like this, we just need to read it slowly and carefully. It's very easy to just skim too fast and miss things. So the three questions we're trying to answer for each of these problems is the first one, what is the thing that we're trying to find? So what do we want to know? What do we know? What things have we been given? The second question is what do we want? What's the thing we're trying to solve? And then we need to decide which equation to use, and then just do a wee bit of maths to figure out what that is. I'm going to do my calculator, so let's just get that out as well. Okay, so first question. We have a car that accelerates at 2 meters per second squared. Okay, so from an initial velocity of -2 meters per second. What is its displacement from its start point after 1 second, 2 seconds, 3 seconds, and 4 seconds? Okay, so we're hopefully going to find something involving those things. So what do we know? Well, let's have a look at it. We know, first off, we're given that the acceleration is 2 meters per second squared, and we're asking the question, is this constant over the whole interval? Would be nothing to suggest otherwise, so we'll go with yes, that's true. So A is equal to 2. And just for economy of space, I'll leave the units off, but we know it's meters per second squared. Initial velocity needs to be meters per second. We have that too. So we know VI is -2. And the other one's a little bit tricky. You may take a second to spot this one. The other thing we've actually been given is we've been given the length of the time interval that we care about. But we've been given a few different values for it, so let's just leave it as delta t without putting a number in just yet and see what happens. And what do we want? Well, we want to know what its displacement is from its start point, so that is our delta x. So now our job is just to look through the kinematic equations that are on the right over there and find the one that relates acceleration, initial velocity, delta t, and delta x. And that is this equation here. It's got those four things in it. Doesn't have final velocity in it, which is good because we don't know anything at this point about the final velocity. Of course we could find it, but that's not what we've been asked to do. So the equation that we want to use is delta x is equal to VI delta t plus half a delta t squared. And we don't have to do any rearranging for this question because it's already telling us, it's already in terms of delta x equals something in terms of the others, so that's fine. So we can just pretty much put the numbers in and hope for the best. So we'll go delta x, let's put the numbers in that we know, and we'll just leave delta t as a variable. So delta x is going to be VI, initial velocity is -2, so -2 delta t plus 1/2 times 2 times delta t squared. So I put in 2 for my acceleration and -2 for my initial velocity. And now to find those various things, let's just go make a little table, delta t and delta x. So after 1 second, 2 seconds, 3 seconds, and 4 seconds. So delta x will be -2 times 1 plus, well, these two here, these just become a 1, right? So let's just ignore that and just make it plus 1 squared, which equals -2 plus 1, which is just -1 meter. So in 1 second, it's gone in the negative direction by 1 meter. After 2 seconds, we'll plug that in there. So it's going to be -2 times 2 now, plus 2 squared. -2 times 2 is -4, plus 4. After 2 seconds, we are back to our starting point. That's interesting. So we must have turned around and be heading back in the opposite direction because we're back to where we started already. So imagine our car, what's happening here is it's kind of reversed a wee bit, and then it's turned around, and now it's going back that way. Okay, and we can do the same kind of thing for time equals 3. negative 2 times 3 plus 3 squared, negative 6 plus 9, which is, it's going to be at plus 3 meters, so it's now kind of over here. And then finally, at 4 seconds, it's going to be negative 2 times 4 plus 4 squared, which is negative 8 plus 16, which is positive 8 meters. Okay, so the first example, this one was not too bad in that we didn't really have to do any rearranging of the equation, but the principle holds and we got ourselves our answer. So let's do another one. So now we have a problem about an accelerating swan. I don't know if you've ever seen a video or in real life of a swan taking off. So basically on a lake, it takes a massive long run up, flapping its wings while it speeds up until it eventually gets going fast enough that it gets into the air. So we're told that our swan must reach a speed of 8 meters per second to take off, and that it accelerates from rest at 0.40 meters per second squared. And we have two things to answer. One, how far will it travel before taking off? And two, how long does it take to become airborne? So first off, we have to look at what it is we know. What have we been given as part of the problem? Well, I can see that we've got this takeoff speed at 8 meters per second. That sounds like the velocity at the end of my interval. So that is my final velocity. I have also been given that my acceleration over the interval is 0.40 meters per second squared. But on the face of it, it looks like that's all we have, because those are the only two numbers that we can see. And I've been saying we need three things in order to be able to make these equations work. So we're going to have to go back to the wording of the problem and look a little more carefully. So if you look a little closer, there's a little phrase that you should look out for, which is from rest. This means at the beginning of the time interval, from rest means it wasn't moving to start with. So quite often this little clause will creep in, so look out for it. What this means is that our initial velocity is 0. Okay, so for the first question, the thing we actually want to find is how far will it travel, so that is our delta x. So now our job is to identify which of the 5 kinematic equations has those 4 quantities in it. That is to say, we want to find the one that does not have delta t. Okay, so not that one, not that one, not that one, not that one. So we're going to use vf squared equals vi squared plus 2a delta x. And let's write this down. Vf squared, vi squared plus 2a delta x. Right, now before we can actually find our answer, we're going to need to rearrange our equation to make it delta x equals something. And generally speaking, while I could put the numbers in now, it's a good habit to get into to rearrange equations in terms of the variables first, because this means you could reuse your rearranged equation with some different numbers later on if you needed to. So we're going to try and establish some good habits, and we'll rearrange our equation before we substitute our numbers in, but it's not wrong to put them in as well. We're just trying to be good humans. So we want to find delta x. So I'm just going to switch it up. So it says vi squared, same equation, just written left and right hand sides reversed. The thing I want is delta x, and so I'm going to just do some operations to this equation to chip away at the pieces that are attached to the delta x until I get it by itself. And just going to remember the golden rule of working with equations is that you have to do the same thing to both sides of the equation in order for it to remain true at each step. So first thing I want to do is I want to get rid of this vi squared from the left hand side, because that's in the way. So what I'll do is I'll subtract this off. Okay, let's just make a little bit more space. I will subtract that off from both sides of my equations. Remember, doing the same thing to both sides. I don't have to think about it, just write down minus vi squared on both sides. Then I'll cancel it off. These two will cancel off because they will just be 0. And so my new equation will be 2a delta x is equal to vf squared. So you should be producing a new equation at every step. I want delta x, so I can get delta x by itself by dividing out that 2a that's multiplying it. So do the same thing on both sides. Well, I've lost my minus vi squared, whoops. So do the same thing on both sides. Now it's really important when you've got multiple pieces on the right here like this, like I have to divide the whole right hand side of my equation by 2a, not just the thing at the right hand side of it. but not just the VI squared. So that should cancel these off because 2a over 2a is just 1. So that'll be 1 times x. So that will give me delta x is equal to vf squared minus vi squared over 2a. Now you may get to that rearrangement in a slightly different way. That's fine. So long as you do the steps correctly, it'll be equivalent to this. And now all I have to do is put my numbers in. So that's going to be 8 squared minus 0 squared, all divided by 2 times 0.4. So that will be 64 over 0.8, which I can see ought to be 80, but let's just put it on the calculator to make sure. 64 divided by 0.8, 80 meters. Now, because we've been given what is on the face of it a plausible word problem to solve, we should also check that our solution that we come up with is physically reasonable. So if you visualize what 80 meters looks like, does that seem kind of about right to you? Well, we haven't found 8,000 meters or sort of 8 millimeters or anything weird like that. So it seems like we're in the right kind of ballpark that would make sense based on our in-depth understanding of how swans work. So we'll be happy with that answer and we'll move on. For our next example, we are going to do the same thing again, but this time we're going to try and find out how long it takes to become airborne. So going over to the next page, we know these things already, we found them, and we also know, we just found delta x was also equal to 80. And we want to know how long it takes, so the thing we want to find is delta t. Now this time we actually have all 5 quantities in play because we know 4 of them already. So we've got the luxury of choice. We can choose whichever equation we like the look of the best. Any of them will give you the right answer. General advice, if you're trying to find delta t and you can avoid using an equation with a squared in it, one of the quadratics, then that's probably a good choice because then you don't need to think about what the 2 different solutions to delta t mean and rule one out. So I'm going to look for the equation that doesn't have a delta t squared. I know I have all the other pieces, so it doesn't matter which one I go for. So it looks like this one here will be the nicest. So I'll get Vf is equal to Vi plus A delta t will be my equation. So let's once again rearrange this for delta t. So Vf equals Vi, leave some space for an operation. I won't, I'll switch the equation around. So I want delta t. So again, I'll change it around. Still the same if you write the left-hand side and the right-hand side is reversed. And I'm going to subtract off Vi from both sides first, because this time I'm trying to chip away at the delta t. So minus Vi, and I'll have A delta t, because the Vi minus Vi is 0, will be Vf minus Vi. And once again, very similar to the previous one, I need to divide the whole thing through by A, and that should get delta t by itself because the delta A over delta A just going to cancel out to give me 1. So delta t is final velocity minus initial velocity divided by A. So putting my numbers in, 8 meters per second minus 0 meters per second divided by 0.4. Again, you could type in your calculator, but I can also see that's the same as 8 divided by 4 times 10. So that's going to be 20 seconds. It takes 20 seconds to become airborne, which was a run-up of 80 meters. And again, to me, that seems plausible. I haven't got an absurdly large or small number, so I'm kind of happy with 20 seconds as my answer there. All right, now what I suggest you do next is you watch this video that I'm going to link in the comments, and I'll also put it on stream. This is a video taken in a massive vacuum chamber where they drop a feather and a bowling ball simultaneously from a great height where there is no air present in the chamber. So I'd recommend you go away and watch this video before we come back to our last example. In fact, let's make that a separate video. We'll see you next time. Ka kite anō.